Okay, our next venture is into the world of geometric isomerism. Geometric isomerism, which is another word for getting diastereomers, which are cis and trans. So recall what we learned about cis and trans isomers. These could be about double bonds, or they could be on a ring. And I told you when the groups are pointing in the same direction, and you don't have to say solid or wedge if it's a double bond, but they are pointing in the same direction, you call it cis. And in case of a ring, of course, then since it's saturated, you do have to show the solid or the wedge. So if the groups are pointing in the same direction, those are cis, and if they're on opposite sides, then you call it trans. Now, the lab in question is going to convert a cis isomer into a trans isomer. So, namely, we are going to begin with maleic acid, which is a cis isomer. We are going to treat it with a mixture of HCl and water, and then convert it into a trans isomer. Since we have to heat this, we have to reflux this. That is the driving force of the reaction. You're providing the heat, you're providing the acid for the reaction to take place, and as the reaction goes through, you end up getting a more stable trans isomer, which is more stable. So the driving force in this reaction is the presence of heat, the presence of acid, and the stability of the product. Those three things essentially account for the stability of the product and the driving force for the reaction. Now, as far as the mechanism of the reaction goes, there is a little bit ambiguity in terms of whether the reaction goes through a free radical mechanism or whether it's a polar reaction, but that's anyways not a part of our aim. We need to just realize that in this particular reaction, we have to go through a bond cleavage. So I'm going to go through one of the plausible mechanisms, and like I said, there's two groups of people in the world who believe two different things happen, and it's a little bit unclear as to how what the mechanistic role is. But definitely there are some things that do not happen in this particular case. So I'll tell you, and there are some things that we understand that there is experimental evidence of. So let's take a look how that goes. Now, first things first, like I said, it's a cis isomer, which is going to give you a trans isomer. And that means that you are carrying out the reaction on the double bond, and so you will need to break that double bond and then reform that double bond. Now, how that HCl adds on that double bond, that is the question. So some people say that goes through a free radical mechanism where the H and the Cl would simply add on in a homolytic sense, but some people argue that since HCl is a polar bond, we won't quite look at it through a homolytic cleavage, but rather a polar reaction. Either way, what you can definitely say is that since this is a cis isomer in which on your double bond you have two electron withdrawing groups, you cannot show a reaction that the double bond is simply going to pick up the proton and Cl is going to leave. That probably will not occur. So the probability for that is remote. So we can throw that particular option out of the window. But what else can happen? Let's take a look. So we have in the first step, as you saw in the mechanism, it says that you're supposed to heat malic acid, 1 gram of malic acid. You're supposed to heat that with water, about 8 milliliters of water, and you're supposed to bring it to a boil. Now, this particular step, you don't have to carry out the boiling part to the T. You can, because the whole idea there is to dissolve malic acid, but as you will see that malic acid will dissolve at room temperature. Most of it would. If it doesn't, if let's say 90-95% of it goes and maybe a little bit of it stays behind, I would suggest heat it. You don't have to wait for it to boil, but you can just warm it up. You can just warm it up for about 5 minutes or so before you add the HCl. So in this particular case, you would say that since you are treating that with HCl, that's positive, that's negative. So one of the oxygens can pick up the proton, and it's going to give you oxygen with the hydrogen, positive charge, OH, COOH. Electrons will move towards itself. These electrons will move. They will ultimately generate a positive charge right over here. Let me number these atoms so you can see. So that's, if that oxygen is position 1, this is 2, this is 3, and that's 4. So you can say that essentially your delocalization of electrons gives you a structure that has a positive charge like that. And now your Cl can come in and it can attack. Also realize in this particular case you have a boatload of water around, so even water can attack because it's a good nucleophile that can attack and give you a malonic acid like species as well. So both of those are possible. This is all in equilibrium. So you're going to end up with, and even if it's water that would attack, we will be able to generate a hydronium ion at the end of the day, and that's a good leaving group, so that's not an issue. Let's say chlorine in this case attacks, and so you end up with a Cl. Notice now that the bond, which was originally a double bond, that area is now a single bond, and it can go through a rotation. So this is going to rotate. This is going to rotate, and then we will reform the double bond. And again, the whole idea is, since the transalkenes are more stable than the cisalkenes, that rotation would be allowed. So as it rotates, you're going to end up with OH, OH, Cl, and COOH. And so now, since Cl is a good leaving group that can leave, electrons will move, lone pair of electrons will be donated. So you will see a structure that looks like oxygen with a positive charge, COOH, and an OH over here. And the Cl or water, one or the other, is going to pick up that proton and release the positive charge on oxygen, so you end up with fumaric acid. Now, a couple things about this reaction. First things first, as you can see, hopefully, that the cis isomer has the like groups on the same side. That makes that molecule pretty polar. And so that is the reason that when you add water, which is the solvent in this case, everything goes in. On the other hand, the trans isomer, it actually precipitates out a lot of times, even when the solution is hot. And the reason for that is because it is fairly non-polar and it does not go into the water, so it will precipitate out. And if it doesn't precipitate out when it's warm, definitely when you cool it in ice, in that step it is going to crash out from the system. So you will be able to simply filter and wash the product and be able to collect it, dry it in the oven, take the melting point, take the IR, and that'll be it. So in this experiment, it's a pretty simple experiment, but you will be dealing with essentially, giving me, at the end of the day, you would be giving me the melting point of maleic acid. And as your reaction is being heated, you guys would be working in the hood, by the way, because you're using HCl. I don't want any fumes outside, so we would be working in the hood, so you would be working in groups of 3. And as you have set up the reaction, I would encourage that one person should get to the melting point apparatus and determine the melting point of maleic acid. You have to give me 3 melting points, at least 2. One melting point is not going to cut it, so you are going to do what you have been doing so far: MP1, MP2, MP3, and then you're going to take an average. If you get a range, report the range. It's only the slow reading that you're going to take, not the fast reading. So the average would be the lower readings, average of that, and then the high readings. So average will be low to high for each of the 3 readings that you have gotten. Now, after you get your precipitate, you're going to filter it on a Buckner funnel. You're going to wash it with water to remove any traces of HCl, and then you're going to just heat it in the oven for about 10 minutes or so, and then so during that time, you should we will provide you the IR of the maleic acid, so you don't have to worry about that. But heat it for about 10 minutes or so that it's as dry as it could be. And then again, one person should engage themselves in getting the melting point of the fumaric acid. And so there'll be 3 melting points from there, MP3 and the average. And then you're going to get an IR of that. So one of the lab partners should engage in getting the IR. Now, about the IR, this IR is going to be a solid IR. So this will be done in mineral oil. Recall what you learned last class. This will be done in that. In terms of the melting point, I should tell you that fumaric acid is it sublimes. So you will need to seal the tube before you begin your melting point. Otherwise, it's going to sublime, so you won't even see anything. It'll just vanish in thin air. So sublimation, recall from general chemistry 1 and 2 that it is that process where the solid gets converted into the gas, into the vapor form, without really going through the liquid phase. And so you won't be able to see it convert into the liquid phase if it's open to the atmosphere. And so for that reason, what we will do is we will powder the sample, the product. We will fill in our capillary tube. So let's say I filled my capillary tube, and then whatever is the open end, we are going to use the microburners. So these are not the regular Bunsen burners that you see in the lab, but these are smaller micro burners. They work exactly the same way, but they are much smaller in size, and so the size of the flame is very little as well. And so you will use that to just seal these capillary tubes before you subject those to the melting point experiment. And once you have your values, you're going to report that in your notebook, and that will be the observation for the product. So you're going to report basically the percentage yield. You're going to report melting point of maleic acid, melting point of fumaric acid, and then IR of maleic acid, and then IR of fumaric acid, and you're going to discuss all of that in your conclusion, and that will make up a complete conclusion section. Answer the post-lab questions, and that will be the lab. Just to recap on the percent yield in case somebody has forgotten, realize in this case you're going from A to B, maleic acid to fumaric acid, and it's 1 mole to 1 mole. In this particular case, since these are isomeric, so the molecular mass is exactly the same, but I'll still go ahead and give you the steps. So 1 gram of maleic acid, whatever is the molar mass, I want you to figure that out. So you will divide that by the molar mass of maleic acid so that you convert it into the moles. And then since the stoichiometric ratio is that 1 mole of maleic acid gives you 1 mole of fumaric acid, and now you're going to multiply it with molecular mass of fumaric acid, because that is equivalent to a mole of, and so the grams and grams are going to cancel off, the moles and moles are going to cancel off, and what remains is going to be your theoretical yield, and the actual yield is what you get from the lab. So actual divided by theoretical times 100 gives you your percent yield. And so this is a pretty successful lab. Otherwise, hopefully you guys are going to maintain the same record as what has been set up by the previous classes. Good luck.